Alright people, here's a quick video to help you with worksheet 4.6b. I'm going to go through the front page and then you can finish up the back page and kind of do the exact same things on here that we're doing on this one. So, that being said, if this is my regular function, here's all the stuff we're going to do for our regular function. We're going to try to find the x-intercepts, the y-intercepts, the end behavior, and any asymptotes. Now, since there's no fraction here, I know you see a fraction, but that's really the same as, negative 1/3. Here's just another way of rewriting the problem, right? So there's none on the asymptotes, and you find that a lot. As long as it's not a fraction problem, we don't have to worry about that. Secondly, we're going to look for x-intercepts, which I said sometimes you can find, sometimes you can't. With this one, you set y equal to 0. So I'm going to go ahead and set this equal to 0, negative 1/3 x cubed plus x squared. And then I can solve this by factoring, actually. This is one you can. Sometimes you can, sometimes you can't. But I can take out an x squared from both these. Negative 1/3 x plus 1. Right? And then I can set this part equal to 0, so one of your x-intercepts is x equals 0. The other x-intercepts is when I solve this one. Move this to the other side, and it becomes positive 1/3 x. And then to undo a 1/3, you multiply by its reciprocal, and x equals 3. You could confirm that by plugging in here and getting your answer. You'll see. So I got two x-intercepts. I can already put them on the graph. There's 0, 1, 2, 3. Already got a couple dots to put on there, right? Next, I can find y-intercepts, which is even easier because you just set x equals 0, plug it in, and it's 0 and 0, so y is 0. Which I already knew. Look, there's the y-intercept. Oops, already found it. All right, now we do the limit thing, and since it's not a fraction, I don't have to do the top-heavy, bottom-heavy cancel thing. I can just think of, remember, when you work with really huge numbers, the x squared doesn't even matter. It just behaves like negative 1/3 x a third. So if I were to put a huge positive number like infinity in there and cube it, it gets even more huge, but then I multiply by negative 1/3, which means it goes to negative infinity. Also known as you go way to the right, this thing goes way down, right? Because these are the x, that's the y. Similarly, if I put in a negative infinity and cube it, a negative times a negative times a negative makes a huge negative, but then I multiply it by negative 1/3, and it becomes a huge positive, which means as I go way left, my graph goes way up. So I already know what my graph's going to look like. It might even help me to just like put a reminder down here. Okay, as I go way to the right, it's going to go down. As I go way to the left, it's going to go up. I might erase that in a little bit if it doesn't line up with my other points, but yeah. So we took care of everything with f of x. Now we want to deal with f prime of x, so I should probably find that, right? So the derivative of this, I'm going to do it with this one because these are c. 3 times negative 1/3 is going to be negative 1 x squared, and then this guy is plus 2x. Okay, or a nicer way to write it, negative x squared plus 2x. All right, so what if I should rewrite this? Why not? Might use it later. Okay, so my first derivative I use to find critical numbers, and critical numbers are when this thing is 0 and when it's undefined. Since it's not a fraction, I'm going to write undefined never. I don't have any times when this could be undefined. I'm not dividing by 0. I do have times when it could be equal to 0, though. And I would solve this by factoring. Why not? Right? When you can factor, factor. I can take out an x from both of these. And with this one, either x equals 0 or x equals 2. Now you could set that equal to 0 and move the x over. So I already have two critical numbers. Remember, these aren't points. These are where my graph is going to split. My table is going to split down here. Next, we have f double prime, which is the derivative of this guy, which would be negative 2x plus 2. Okay, inflection points are where this thing equals 0. And kind of like before, I move this to the other side, divide by 2, and you get 1. So I know my graph is going to split at 0, 2, and 1. So when I make my table, I have my interval, my test point, my f prime of x, which is increasing or decreasing, my double prime, which is the concave up or concave down, and then I have a sketch. So I have to know to split this 3 times. 1, 2, 3. And I have to be careful that I put them in number order. So start with the smallest. So this is x equals 0. Here's 1, and here's 2. And then my intervals from negative infinity to 0, from 0 to 1, from 1 to 2, and from 2 to infinity. Okay? So my test points, some of them are going to be nice, some aren't. I would test negative 1 because it's small. Here you got to get, it's going to be kind of ugly, 0.5. Here, 1.5. I mean, you could use any number between there. And here, how about 3? All right, so I got some points to test, and I'm testing them in these. So right now I'm going to take a negative 1. I'm going to plug it in up here. So negative 1 squared is 1, and then I attach a negative sign to it, because remember, only the x is being squared. So it's worth negative 1, and then 2 times negative 1 is negative 2. Negative 1 plus negative 2 is negative 3. I don't really care that it's negative 3, I care that it's negative. You can type that in your calculator, just use parentheses. I would always use parentheses. You plug in a 0.5, I'm going to get negative 1/4 plus 1, which would be a positive. You plug in a 1.5, I'll have to type that in. Let me not waste time on the video. So if I plug a 1.5 into the original, or into the derivative, I get a positive 0.75. I don't care that it's positive. I care that it's, or I don't care that it's 0.75. I care that it's positive. Last but not least, I put a 3 in here. You'll get negative 9 plus 6 is a negative 3, but I care that it's negative. So right away, I know that my graph is increasing from here to here. I know, or sorry, decreasing, geez, because it's negative. It's increasing between 0 and 1. It's increasing between 1 and 2, and it's decreasing forever to the right. We're going to do the same thing on the double prime. So here we're going to plug in a negative 1, and if we put in a negative 1 here, you're going to get 2 plus 2 is 4, but it's positive 4, so that's concave up. We're going to plug in a half. You put in a half here, you get negative 1 plus 2 is 1. That's positive. That's concave up. We plug in a 1.5, you're going to get a bigger negative number here than 2. So it's negative. That's concave down. And last but not least, you put a 3 in here and you get another negative. It's pretty typical for these to be symmetrical. So if I draw a picture of decreasing concave up, remember I draw a stick for decreasing, and then I bend it so it's concave up. So it's going to look like this for that whole chunk of graph. Here it's increasing, so my stick goes up. Then I bend it so it's up like a cup, concave up. Okay, and then I have increasing but concave down, so I curve it down. And last I have decreasing stick, concave down. Alright, so that's that. Now I gotta draw it, but other important points are max and mins. So do you see how it goes from down to up? Well, there's a min right there at 0, something. I also know, because it goes up to down, that there is a max at 2, see how it goes like that, 2 comma something. And I forgot to do it earlier, but there's an inflection point at 1 comma something. We never found that point. I just knew there was a point there. But I'll do it all at once, because how do I find the y value every time? Well, you go to your y equals equation way up here, or this guy. Okay, so you're just going to take some time, plug in a 0, plug in a 2, plug in a 1, and you'll get 3 different answers for points. So I'm going to do that off camera so it doesn't waste time. So when I plug those in, I got these numbers here. And these are cool because I have more dots to draw. I know the shape of my graph, but I need some dots to hit. So 0, 0 is already on there. 2 comma 1.3 repeating. 2, 1.3 is right there. That's a max. There's an inflection point at 1 comma 0.6 repeating. So here's 1. That's about 0.6. So that's where it switches from concave up to concave down. Now, if that's not enough picture for you, see how I know it goes up here and down here? And if I know cubes, it's going to have that like snake-like S. But if you ever don't feel comfortable with, it feels like I don't have enough points, I might put in a -1, or I might put in a 4, just so I get an idea where the dots are going. You should always make some extra points just so you know where you're plotting. So I want to go one more to the left to make sure I have an idea, and one more to the right. And I'm plugging these into the original equation again. And so I just go back in my history, and I change these to a 4. Right? Oh, you can't see that, but this is the original equation, so I'm getting y values. If I plug in a 4, I get a -5.3 repeating. Okay, if I go back and plug in a -1, shoot, okay, -1, okay, and then do it again here, okay, and I can see it's going up to 1.3 repeating. Alright, so I can put those 2 dots on here. -1, 1.3, and 4, -5, 5.3 repeating. So you can kind of get a better idea of that graph. Now I know it's going like this. See it, look, it behaves like this curve. It behaves like this whole curve until you get to 0, 0. Okay, so it's curved down, 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 down until there. And then between 0, 0 and 1, it looks like this. So I'm going to go from here like that. And then it switches over to be curvy down from 0 to 1, which is a pretty quick turnaround. And from here on out, it looks like that. So the graph is kind of made for you. You just need some dots to draw through. Right? Boom. Look at that beauty. She's a beauty. Oh. And just to prove to you I'm not, lying to you, maybe I'll erase these things. I'm going to type that into my graphing calculator and see what the graph looks like if we made a beautiful graph using calculus. So I just typed the original equation in, I hit graph, look at that thing. Man, it does not get much better than that. Look at that, that's beautiful. Okay, so calculus is pretty cool for doing all this. You're going to do the same stuff on the back with a new equation. All right, and I will talk to you later. Hope that helps.